Good afternoon, everybody. My name is Gautam Das. I'm the Associate Dean for Research, the College of Engineering at UTA. Welcome to our Friday brown bag, virtual brown bag series. We have an exciting presentation, an exciting talk today by one of our very own, Professor Seong Ko, who is a professor in the Material Sciences and Engineering Department. And the title of his talk is going to be Engineering on a Nanoscale Level, from Manipulating Single Electrons to Detecting COVID-19 RNA. So a little bit of introduction in case you don't know who the speaker is. So he's a professor, as I said, in the MSc department at UTA. His research interests include investigating cold electron transistors for extremely energy efficient electronics, large-scale manipulation of nanoscale building blocks for bottom-up construction of functional materials, and direct detection of single molecules of DNA, RNA, antigens, and antibodies. He received his PhD from UIUC, University of Illinois Urbana-Champaign, and his MS and BS degrees from Seoul National University in Korea. He joined UTA in 2003, but before that he worked at Bell Labs, Lucent Technologies, where he was working on integrated circuits. He is very celebrated research published in high-impact journals, including Nature Nanotechnology, Nature Communications, and Physical Review Letters. He is a recipient of the Career Award from the National Science Foundation, a very prestigious award, and recipient of the Outstanding Young Faculty Award from UTA's College of Engineering. He has several patents also to his name. So I'm going to welcome Dr. Ko to start the presentation, but just wanted to lay out some of the some of the directives by which we're running this talk. He'll give his presentation, and then we'll have a Q&A session towards the end. And if you have any questions that you want to ask, please feel to type them into the chat box, and I'll be keeping an eye on them as a host, and I will read them out to the presenter, Dr. Ko, and he will answer them. So hopefully we'll have an exciting session today. So Dr. Ko, please, it's up to you now.
All right, thank you very much, Dr. Das, for your nice introduction. And I was told that these brown bag seminars are for general public, so I tried that this presentation slide as simple as possible. I found that that's not that easy job, but I tried my best, and I hope that you enjoy this talk. So first of all, I'd like to, because again, this is for general public folks. Maybe many of you may not know what is material science and engineering, so I'll give you a brief introduction. Actually, this slide is made by Professor Chung-Won Kim in our department. So as you can see, hopefully you see my cursor, that all this human evolution and is by mastery of materials. As you can see, you have Stone Ages, Bronze Ages, and the Iron Ages, and now you have Information Ages. All of them has been possible because of new development of materials. So the materials key. Without material, like all the economy, power of economy, military power, all depends on the materials and how to develop good materials. And what we are doing in our department is that we are dealing with all the materials. Materials are everywhere, and we have different structures, processing, properties, performances. And materials include everything basically. For example, metals, ceramics, concrete, and electronic materials, polymers, and biomaterials. And we engineer the materials. For example, you see the aluminum can is made of aluminum. This is very you can actually crush them using your hand, right? Very soft. Same thing this aircraft is made of aluminum alloy, and if you put the atoms like a zinc, copper, or magnesium into the aluminum matrix, you can have very light but very strong aluminum alloy can be produced. And this is silicon. Silicon is abundant. All the sands on the beach are made of silicon. And out of that, we can produce silicon substrate, and we can actually manufacture many electronic circuits. And all the electronic devices that you have, your laptops, iPhones, smartphones, or tablets, inside there is electronic circuit. It's all made of silicon. So in our department, there are many exciting researches are ongoing, and today I'd like to just talk about some of research that my group is carrying on. And I'll talk about 3 topics today. The first topic is manipulating single electrons. So we are talking about how to move add one electron at a time. So and you can make also out of that you can make single electron transistors. And next I'll talk about the cold electron transport. So you can cool electrons to very low temperatures without actually using any coolant. And also I'll talk about detecting COVID-19, which is very important these days. We want to have very fast, cost-effective detection of COVID-19. Okay. So first topic is single electron transport. So ultimate goal of your electron devices is actually you have electrons are flowing right in your device. The ultimate manipulation will be we can just control the flow of electron just one by one. Can that be possible? Yes. So how can you do that? So first think about this one is think about some sphere made of metal, and think about just one single electron. And think about when we just add this one electron to this metal, and it turned out that the energy to add one electron to this metal sphere, we call that single electron charging energy, will depend on inversely proportional to this radius of this sphere. So electron will have, even at room temperature, certain energy. So if that electron, charging energy, the energy to add one electron to the sphere is very low, obviously it will be very low if your diameter is very large, right? If you have a large this sphere, metal sphere, the energy of this single electron, even at room temperature, is high enough so that we can add electrons to this largest metal sphere. But as you can see, that energy will be inversely proportional to the radius. So if you make this metal sphere very small, then what happens is that the energy to add one electron to this very small sphere, metal sphere, will be enormously large. If that happens, electron cannot actually be added to this small metal island, and we call that Coulomb blockade. So then that can be utilized to actually control the addition or subtraction of single electrons to this small, we'll say, islands, and we call these small spheres we call Coulomb island. So that's a very, basic principle of how to control, how to manipulate single electron transport. If you make this one, the energy, charging energy is extremely large, then we can actually block the addition of single electrons to this small sphere. Then we can control that addition and subtraction of even single electrons. How small is small? We are talking about the size of at least 10 nanometers or below. Okay, so 10 nanometers. So nanometers is actually billions of meters. It's very, very small. So when you say 10 nanometers of sphere, let's say this metal sphere is made of gold. So if this is 10 nanometer here, diameter is 10 nanometer, that means, and gold atoms, between gold atomic spacing, we call the lattice constant of gold atom is just 0.4 nanometers. So within this 10 nanometer, we have only about 25 gold atoms. And that means in the three-dimensional case, this sphere, we have only this 10 nanometer gold sphere is made of only 8,000 gold atoms. So just give you the impression how the idea how small the Coulomb island should be. So once we can make this small sphere, and we can actually the addition of single electron to this Coulomb island can be controlled, and by doing so, we can actually manipulate the electron flow one by one. So hopefully that this explains the concept. So we have a Coulomb blockade, so this cannot be easily, there is some energy barriers so that we cannot add the single electrons to this metal island. So we can make a circuit out of this. So this one is made of very small, the metal sphere, at least 10 nanometer or below. And it's, we call this Coulomb island. And we have the one electrode we call source, and we have the other electrode we call drain. And we apply some voltage bias. And then, and we make a very thin layer, we call that tunneling barrier, which is about 1 or 2 nanometers thin, very, very small. Then if you adjust this voltage, then we can adjust the energy environment of this Coulomb island, so that even if let's say we don't apply any voltage, then the electron cannot actually go in because of this large charging energy, right? We call that Coulomb blockade. But by controlling this bias, we can have it good enough that one electron can actually add it. So by doing so, you can add just one electron to the Coulomb island. Or we can actually subtract one electron out of that. So it's now possible just because of that, the adding one electron to the Coulomb island can be, can be easily controlled. So if you increase voltage, we can add one more electron to this island. So we can actually we can control the exact number of the electrons in the Coulomb island, and also we can control. So we can just add one electron and take out one electron, or we can add 2 electrons and take out electron one by one. So all of that can be possible. And if you do so, then we can have this the voltage current relationship. So usually, if you have IV, right, if increased voltage, it should be linear. But in this case, if there is this single electron behavior is going on, then you can have this staircase. So we call this Coulomb staircase, and that represent this plateau represent we have extra electrons in this range. So we just add, if you just add one electron here, you can just adjust your the voltage here, then you will have just one electron on the Coulomb island. If you want to add just two electrons, you can do so by adjusting your voltage in this range. Also, you can take out your electrons out of this one by one, and more. So you can add one electron, two electrons. If you want, you can subtract one electron out of this Coulomb island. So we have a total control of the electron in the single electron level, one by one. So, but the fabrication of this single electron device is not that simple. So you can see, we are talking about the really nanoscale dimension. Think, as I mentioned, this tunneling barrier, the thickness is 1 or 2 nanometers. 1 nanometer is usually the atomic size. Atom size is just between 0.2 or 0.4 nanometers. Gold atom case is 0.4 nanometers. So 1 nanometer or 2 nanometers, we are talking about, very few atoms distance between this electrode and Coulomb island. So how can you, the fabrication of that is not that simple. And also, as you can see, the Coulomb island should be exactly placed between this source and drain. And so this needs very, very sophisticated nanoscale fabrication. So to do that, so again, we need the couple of nanometers of spacing here. And of course, Coulomb island should be less than 10 nanometers, and then must be exactly placed between source and drain electrode. So how can you do that? How can you fabricate them? So think about your pen. So there is pen, and you write. So you may just fabricate using some tool laterally, and make some pattern. Think about that. But you know that this pen size, this lateral size, even if this is very sharp pen, let's say this is in atomic scale, we cannot make something just with a single atom. There should be some atoms there. So if you want to try to make something in lateral way, the resolution it's almost impossible to make something below 10 nanometers. Okay, so then, as I mentioned, this spacing here should be a couple of nanometers. So there is no way to pattern them and make it. The other way is that you can use something clever way that use vertical configuration. Let's say this is a cross-sectional view, side view. Let's say you have a substrate, but we can add a very thin layer of atoms or thin layer of materials and just deposit something on top of this substrate, and the layer thickness can be controlled in the sub-nanometer level. So this can be very precise. So you can actually deposit just a few atoms, atomic layers, on top of this substrate. And then we can deposit another one. So if you look at the sideway, the cross section, actually you can create very precise dimension, right? And if you use the vertical configuration. So in this case, the resolution can be below 1 nanometers, right? So that's the concept that we are using to fabricate our single electron device. So this one is our structure, how we made. So in this case, source is that the material. So this one is a vertical configuration. If you look at back, the source material and drain is actually vertically. The configuration is done in the vertical way. So key of here is that as I mentioned, this should be nanoscale, right? And because we can control this height in sub-nanometer precision, we can actually make it the circuit if you use this film thickness, and if you can use the sidewall of this configuration. So, for example, you can put the 10 nanometer gold nanoparticles at the sidewall, and you actually have a circuit here, and the distance between this source and drain can be exactly controlled. So the benefit of that one is also we can do this one in the large scale, because you can deposit these very thin films over the large area, actually entire area of the wafer. That's our concept, and actually we fabricate this device in our university and NanoFab. So this is in-house fabrication, and I won't go in detail, but we had made the single electron transistor out of that, and we use this one using the conventional, actually the electronic circuit manufacturing process, and it's a totally parallel fabrication. So now this is our result. As you can see, what is it? The point is that we use the vertical configuration so that the separation of source and drain can be exactly controlled. And by doing so, we were able to make the circuit, and by applying voltage and bias, we can add one electron and subtract one electron. So you can control the flow of electrons on a single electron level. As you can see, this the voltage and current characteristics. The signature of single electron transport is Coulomb staircase, as you can see. So this means that no electrons. This one is additional 1 electrons, additional 2 electrons, additional 3 electrons, and this one is 1 electron is subtracted from this Coulomb island. 2 electrons is subtracted, 3 electrons. So from this one, we can just control the number of electrons in the Coulomb island, and we can actually flow electrons one by one in a very, very precise way. So previously, we just had a two-terminal device. If we go back, we have only source and drain, right? And there is something called electronic circuit called transistors. And for that, we have additional gate, and this gate electrode actually controls the flow of single electrons. So that we call a single electron transistor, and we have fabricated that. This is the plot, the simplified diagram of this single electron transistor. So you can see here the source and drain is separated by a very, very thin layer, because this is vertical configuration, and we can have add gate, and we were able to make a single electron transistors. So this one is a signature of single electron transistors. This one is gate voltage. In other words, we apply gate voltage and control the flow of single electron one by one, and this peak corresponds to adding 1 electron to the island, adding another electron, adding the other electron. As you can see, this one we were able to see this single electron transistor behavior even at room temperature. And as I mentioned, that we were able to fabricate this in a parallel way. So we were able to make them a lot for one batch. And there's 10 different devices, and we measured this, the oscillation, what is that? The delta GV, so the distance between two peaks, single electron Coulomb oscillation peaks. And with different devices, we see that very consistent behavior, so that this proves that we are able to fabricate them in a single batch on a large scale. So many devices can be fabricated at one time. All right, so hopefully with this, so we are able to introduce the concept of how can we control the flow of single electrons. That all started with the concept of charging energy. If that the island is very, very small, electron cannot be added easily, right? Because of there is a very high charging energy. And by controlling them, we can actually manipulate the flow of single electrons one by one. Now the next topic is called electron transport. So currently, the transistors that we are using in the laptops, the phones, and so on, actually consumes a lot of energy. That means it generates a lot of heat. So this is nowadays this is not possible that because of COVID, but long time back, at least one years ago, we see that this is power station at the airport. All the device is power hungry, so you have to charge very, very frequently. Why? Because the laptops and phones consume a lot of energy. This is the data center, Google data center. There are a lot of transistors, and it generates a lot of heat, a lot of energy. So they have to cool this, with water or coolant, and sometimes some may say that we may need to construct this data center in the Arctic, so that in very cold environments, so that we can cool this heat generated these transistors. So bottom line is that current transistors consume a lot of energy. So first of all, then why that transistors consume a lot of energy? Is there any way that we can make transistors that can operate with very, very little energy? So to answer that question, let's think about temperatures. See that, as you can see, let's think about hot air. This is air molecule, and this cold air. And hot air, you see that it moves very, very fast, right? And so if temperature is high, we have high energy gas molecules. If temperature is low, we have low energy gas molecules. If you look at the energy scale here, when the air is hot, we have high energy gas molecules. So the energy distribution is at the higher energy, located at higher energy in this diagram. And cold, for the cold air, most of these air molecules, like nitrogen and oxygen, right? They move much slowly, so that your energy will be on the bottom side. Okay, same thing is that happen for electrons. So let's look at the transistor. Transistor is all any electronic devices. The core part of that is transistor. Transistor is simply just on-off switch. Let's think about this one. Let's say this blue one is actually water flow. Okay, water flow from high energy state to low energy state. What if you have a block, there's some barrier there, then water cannot flow, right? So if you don't have any barrier, water can flow. If you have a barrier, water cannot flow. So this switch can be turned on and off, right? Same thing is true conceptually for electron case. We have on means we have means there is no barrier. So as you can see on state, we have no barrier. So electrons can actually flow from high energy state to low energy state. Off state means you have a barrier, like you can see here, energy barrier. So water should not go over this barrier, so there is no water flow. So in this case, off state, there is a barrier, so there should be no electron flow. But problem is this. So the problem of all this large power consumption of the transistors in your laptops and phones is because of these hot electrons. As I mentioned, even at room temperature, some of them may have higher energy. So we call that hot electrons. That electron can overcome this barrier. In other words, in this case, the water here can by some reason excited, there's enough energy so it can overflow. And that's the origin of all this excessive power consumption of our devices. So if we prevent the hot electron, if we block this hot electron, we can have a much lower power consumption. And even it's predicted that power consumption can be reduced to the 1% of current power consumption of the transistors. So if we can block this high electron, high energy electrons, and so that overcomes this, and we can block that. Actually, if you reduce your power consumption to 1%, that means your laptop, smartphones can last for weeks without recharging. I charge my iPhone every night. That means if you can block these hot electrons, right, flowing over overcome this barrier, that means power consumption increases by 100 times. That means we can actually charge our iPhones or laptops every few weeks or even every month. So this is the idea, and how can block these hot electrons. So let's think about see this baby scroll, and let's say there is a wall here, and to overcome this, that scroll should gain energy, right, to go all the way to the top and overcome this wall. And we call that high energy scroll. I'll call that hot scroll. Or if you have another ladder which has only one step here, then what will happen? You can go there. There is no way to go. Only way is going to this step here. Then this scroll cannot overcome this barrier. There is a way to reduce this wall. Then what will happen is that this scroll will go this way because there is a step here, and can overcome the barrier. And I'll call that this one is low energy scroll, or cold scroll. So exactly the same thing can happen for electrons. So in this case, think about this, that is, I would say, some barrier. Electron can go through this one. This, you see that the color is different. Here is lightly shaded. That means electrons are excited, so that some electrons are in high energy state here. So in this case, high energy state electrons can go through. This is like this scroll in this case. So the scroll gets some energy, and overcome the barrier. So this one is, even if it's, so there is some excited electrons go through there, then what happens is that your IV characteristic, there is a smearing of this, the IV behavior. However, if you put some state, it's same as this one here, ladder, which has one step much below, then as you can see, electrons only in this energy, which is cold, because hot electrons cannot go through, then only cold electrons can go through. Like this low energy cold scroll. That means we can block all the high energy electrons and only low energy electrons, cold electron can go through. So that's if that can work, our problem was here to prevent the flow of hot electrons to overcoming the barrier. We can do that as this example by putting the low energy, low step ladder here. We can do the exact same thing in our devices. Of course, this is much more complicated. We are using some called quantum well. And we can do that in our case. We did that by using this configuration. So this one is the source, and we have some here. We have a quantum well is formed. That barrier is correspond to this one energy state, which is correspond to this low step ladder here, and then we can only allow the cold electrons to go through. So this one we fabricate them. So this is our result. As you can see, we have even like room temperature. See that room temperature, there is a lot of high energy electrons still, but that will be all blocked out, and only cold electron will go through, and we have a very sharp peak here. If there was no quantum well, in other words, there is no ladder, as I showed here. If there is no ladder, the low step ladder here, that's actually we call energy filter. Then what will happen is that at room temperature, we don't see any step because it's all smeared out. Only when you cool the entire device to 45 Kelvin. 45 Kelvin is in degrees Celsius is minus 228 degrees. Then we'll have a same result. So this one is then we can obtain this cooling effect, which is minus 228 degrees Celsius, by just introducing this low step ladder, which is quantum well state. We can produce that even at room temperature. How significant it is? It's very, very significant. This is apple-to-apple comparison of the experiment by others and ours. This one, we can make this transport without any energy filter at the cold electron, without blocking hot electrons. In this case, this one is IV characteristics of the cadmium selenide quantum dot. And as you can see, and this one can be only obtained when we cool the entire system to a very, very low temperature called 4.5 Kelvin. Kelvin is the unit that we use. We call this absolute temperature, which corresponds to minus 268.5 degrees Celsius. On the other hand, exactly the same result can be obtained at room temperature, which means by just introducing the quantum well, in other words, the low step ladder, we can make a same, it can get same IV characteristics without cooling. So think about that. If you cool like 0.5 Kelvin, that means we need to use liquid helium. we may not carry liquid helium all the time to operate our laptops or iPhones, right? So and this is I think very significant accomplishment. So we expect that there are many applications. One is that using that cold electron transport for single electron devices. So we can do that. We fabricate them and see that this is you see that familiar with this single Coulomb staircase. Each one of these steps correspond to addition of 1 electron, 2 electrons, and so on. You can see that we see this Coulomb staircase even at room temperature, because by introducing the lower the step ladder, we call the energy filter or quantum well energy filter, we are able to cool electrons to minus 228 degrees without cooling, without physically cooling it. And same thing, we call this Coulomb oscillations. This is addition of 1 electron, 2 electrons, and 3 electrons. We can observe that even at room temperature. What is the next step? Called cold electron transistor. So we can make this cold electron using silicon-based transistor. So all these devices in your gadgets, electronic gadgets, is made of silicon. So if you do so, we can have a practical application of this cold electron transport. Hopefully, we can have transistors that can consume very little power. Okay, let's move to the last topic of COVID-19 detection. So you may saw this COVID-19 virus many times in the news outlets and so on. And if you look at that COVID-19 virus, inside there is the RNA. RNA contains all this information how to replicate the virus again and again, and we can extract that RNA, and actually convert to some DNA called complementary DNA. And part of this red area can be amplified, because if you have just one virus, then we just have one RNA. So that's very low concentration, is very difficult to detect. So there is some way to copy them, we call PCR. So this one can be copied, then it will be 1 becomes 2, and copied again using the method called PCR. Then 2 becomes 4, 4 becomes 8, and if you do many times, we can have 2 to power n copies. So if you do like 30 cycles, you can have billions of copies. And if you have the billions of copies, it can be easily detected. Problem here is that this is time consuming. We have many cycles. It takes a few hours, and we need bulky equipment, and this is not good for point of care diagnosis. We need a very fast detection on site. So our concept is this. So let's have a COVID-19, and we have some nanoparticle, and here there is DNA which matches with this COVID-19 DNA or RNA, and another one here, and put just prove that with some circuit, just a very small needle. If you do so, you can directly detect COVID-19 without any amplification, and also you can have electrical detection is possible. So in this case, we have just one COVID-19 sequence here, but we can have many here. In that case, it will be like that. So we have one nanoparticle here, and between them, the COVID-19 sequence is captured. So, and this is our result, and we see that this is the image of scanning electron microscope. This one is like a microscope, but we are using electrons, which gives much higher resolution. As you can see, the scale here is just 50 nanometers. So this is 50 nanometer gold nanoparticles. Between them, this is 30 nanometer. We have the COVID-19 DNA sequence was captured. So you can see, so this actually, our concept is basically working very well. And this doesn't work, this works for COVID-19, but any sequence can be used. For example, if you want to detect an anthrax, there is a specific sequence, and you can design this nanoparticle, and this DNA can match with this specific sequence of this anthrax DNA. Then we can do the same thing. Only difference is that the sequence here, should match with this anthrax DNA sequence. By doing so, we can do the same thing. This one is done, the SEM image. This one is, between them is anthrax DNA sequence. In this case, we used a smaller here, and this one is larger one. And we have this anthrax DNA between, and we have that one. And we can, if you make that one, we can do just put some electrode and detect. So we are able to do that. I cannot show in detail because it's proprietary information, at least for now. So I'll just show our final result that you can detect electrically. And this is our size of this the detection chip. It's very small. How about assay time? We can do this at this case in 6 minutes. It doesn't include that extraction of the DNA from the virus, but the assay time, the capture of that is just 6 minutes. Cost is currently in our lab is about $5. Of course, if it's mass produced, it should be almost should be less than $1. And also, as I mentioned, this is very small, and you can detect any sequence. So you can make multiplex detection on a single chip. So for example, this scale, you can see that 5 centimeters, 2 inch and 2 inch, you can make this, this section can be COVID detection, anthrax, Zika, HIV, E. coli, many diseases can be detected at the same time. Because if this dimension is less than a credit card size. Okay, so in summary, I showed that we are able to control the flow of electrons in a single electron level, and we were able to cool electrons to minus 228 degrees without any coolant, and we were able to detect COVID-19 anthrax electronically, and so this is very promising method, and we are currently working on. With that, I'd like to thank all the people who contributed this work, and I want to thank the funding agencies for the National Science Foundation and Office of Naval Research. With that, thank you for your attention.
Thank you so much. This is a fantastic presentation of all the exciting work that you're doing. To the audience, we have about 10 minutes. We'd welcome questions from you. If you have any questions, please feel free to write them in the chat box, and I will read them out to Dr. Ko when I get a chance. So while we're waiting for the audience to pose some questions, I found the talk very intriguing, and I myself have a few questions for you. So the single electron transfer. Again, I may be an engineer, but this area is very far from my own expertise, so I may be asking some very naive questions. Is it? I mean, is it something that has been commercially done now, or is it a future technology? Where are we in the pipeline?
No, it's not commercially done. It's a future technology. So as I mentioned, it's very difficult to to fabricate like 1 or 2 nanometers of the tunneling barriers, and plus you need to put the Coulomb island, very small size of metal island, exact place that we want, right? So we have demonstrated that it can be done in parallel, but it's not yet in the range of mass production or something like that. It's in the future technology.
So it will eventually give rise to even more massive miniaturization of electronics than what is currently possible. Is that the main goal?
Yeah, of course, all the technology has pro and cons. This one, the current flow is a little bit small compared to current the mainstream devices, so that need to be figured out. But on the other hand, you can think about that with the very small electrons, you can control. I mean, everything can be miniaturized, so that I mean, it's possible that a real device can be made. But at this stage, is not commercialization stage, and it's ongoing research.
I see. Okay. So so I have a question. Well, let me complete my other question before I sort of go to the audience, because I'm very curious about this one. So there is this Moore's law which controls the speed at which things can happen, right? Yeah. So will that have any effect on this miniaturization goal, or is that not connected?
Yes. So actually, the first topic and second topic is actually correlated. We started with the first single electron transistor investigation, and we learned a lot, and we learned that electrons can be cooled, right? The second one can be actually mass produced, and that's our focus now. Okay. Because we demonstrate that electrons can be cooled to minus 228 degrees at room temperature without any coolant, right? That can be used for if that can be implemented with current the silicon-based device, right? And that's possible. There's mass production is possible, and that's actually current our the ambitious goal, and we are working on that right now.
So, so will that give rise to low energy consuming, personal electronics, such as?
Yes. So that's the goal is that we want the device that consumes less energy. For as I mentioned, if this is successful, we can reduce the power consumption to just 1%. So think about that. Instead of you have a battery life maybe 1 day for your cell phone. If you consume just 1% of energy, right, your battery life will be 100 times more, right? Yep. So even like 10 times more, that will be huge.
Yeah. So. Yeah. So this can be extremely, disruptive technology if it becomes a reality. That's fantastic.
Yes.
So we have a question from the audience. Kendra Wallace asks, what's the current status of your COVID research? I guess.
COVID research, as I showed you, we had and proven. Let me show you the slide. Maybe. Yeah, we proved the basic things now. So how long will it take to make it all? When basic things means we show that COVID can be captured between 2 nanoparticles, and we demonstrate that actually we can. I didn't show you, as I mentioned, the detail. We can actually put 2 kind of needles to 2 nanoparticles, so we can actually detect the existence of this COVID-19. But still, we did not I mean, so all the concept is now proven. How long will it take to be commercialized? We don't know, and because commercialization is so the different story, right? So, but all concept is proven, and we are working on now very hard, actually.
So, what would be the main advantages over existing, I guess, antigens and PCR kind
Yeah,
of?
there are many other technologies using like antigen can be one thing, and but what we are focusing is that PCR is gold standard, right? Most accurate. That's most accurate, but it requires a lot of time and a lot of equipment and resources, and need the skilled personnel. But we can actually bypass that while still keeping the accuracy, right?
I see. Okay. So you mentioned that some of the details you cannot reveal. Is it because you're working with a private entity or something? Which
No, because it's the UTA proprietary information, so it's on the patent stage now.
oh, okay, I got you. All right, exciting. Yeah.
But it's working, but I cannot present them.
Okay. All right. So just we have a few more minutes left, so I just wanted to give you the chance to maybe have some closing words, like maybe you want to chat a little bit about something else that you're doing. I know you've covered a lot of different things.
I don't know who are these audience who are listening. If you're the undergraduate students, that'll be best. And our material science engineering, as I mentioned, is a future of engineering. Maybe you say the computer science, maybe future of engineering.
I think they're all very important. I think
so. Exciting research is ongoing in the MSc departments. So if you're interested in, you can contact our faculties, and we want to have very energetic young people join us to do this exciting research. That will be great.
So we do have some more questions from Kendra. So let me use the remaining 1 or 2 minutes for that. So she's asking the stuff that is under patent, so it won't be published until it is commercially produced. I don't think that's true. You can, once the patent application is pending, you can start publicizing, right?
Yes, we didn't publish yet.
Okay, so it has not been published.
So maybe it will be soon. Maybe soon it will be published.
Okay. And another question was, can the cold electron devices be applied to smart homes and potentially reduce home consumption?
It can be down to atomic scale, yes, right. But some people did it, but that requires very low temperature. Usually, you need cool. So it can go to atomic level, yes, but that may not be practical, though. Right. But in our device, actually, it was done at room temperature and could be much more practical.
Okay. All right. So I think I would like to take this opportunity to thank Dr. Ko again for a very fascinating discussion into some of the very cutting edge high technology problems in material science that he is doing, and things which are futuristic as well as something which is very current, especially the COVID-19 testing. So thank you again, and I look forward to hearing about your work as we go along in this. For the rest of the audience, we will be continuing this Friday talks. So I look forward to welcoming everybody in the future Fridays. Thank you, everyone. Bye-bye.
Thank you very much. Thank you, everyone.
Thank you.